Hello and thanks for watching this talk. So this is going to be a short presentation of my paper Indeterminism and the C-Theory, Directed Laws and Directionless Time. And the main question that I pose in this paper is the following. Can a theory be indeterministic without implying that time in some sense has a direction? Now at first glance these two concepts, indeterminism and time directionality, do appear to be quite independent of each other. But nonetheless, various authors have argued that in some way or another, indeterministic laws imply that time does have a direction. I'm going to call this group of arguments the one-way applicability argument, and I'll look at various ways in which this has been put forward by authors such as Satoshi Watanabe, Elliot Sober, Roger Penrose and Frank Arnsenius. And the rough idea is that if a law is both probabilistic and time translation invariant, then it must also be temporally unidirectional. It must apply only in one direction in time, namely towards what we call the future. And hence, it supposedly follows that time has, in some sense, a basic or objective or privileged direction. So firstly, we'll look at exactly what the one-way applicability argument is in its various guises. So in what sense do transitional probabilities indicate that the world is indeed governed or best described by time-directed laws? And then in the second part, we'll look at what exactly the direction of time is. And I'm going to look at it from the perspective of my own preferred theory of time, which I call the C-theory of time. Now, the C-theory of time is a temporally adirectional metaphysics. It holds that time does not have a direction. So I'll approach this issue by looking at exactly what it means to give up the idea that time has a direction. And then in the third part, we're going to put these together. We're going to see in what sense the one-way applicability argument raises problems for the C-theory. And I'm going to argue that the C-theory is indeed perfectly consistent with the existence of time-directed laws, and I'm going to make use of an idea which was defended by Hans Reichenbach in his final and ultimately unfinished book, The Direction of Time. And I'm going to build a little bit on some ideas of Reichenbach here to show us how the C-theorist can best make sense of the existence of time-directed laws. And I'll finally look at a related question, which is whether or not the time asymmetry of transitional probabilities can be due to a time-biased way in which we ordinarily think of statistics. So first we can look at what this one-way applicability argument is. So Satoshi Watanabe, in his paper Conditional Probability in Physics, says that if we can use transitional probabilities as a statistical law in one direction of the parameter t, then we cannot apply them in the opposite direction. So if we have some set of time translation invariant transitional probabilities which apply towards the future, then we cannot have the same kinds of sets of probabilities that also apply towards the past. And he takes this one-wayness of probabilistic laws to ultimately trump things like the reversibility, objection and recurrence theorems in the foundations of statistical mechanics. This, he says, gives a simple explanation to the entropy principle. Ultimately, he thinks that this theorem gives some broader explanation as to why entropy gives a monotonic gradient. It only increases and does not decrease across time. Elliot Sober says that a system whose expected state changes with time cannot have both a forward-directed translationally invariant probabilistic law and a backward-directed translation invariant law. Science seems to favour the former. So again, if we have this idea of some probabilistic law which is time translation invariant, so it consistently applies across time, its very existence ultimately precludes a backwards-directed equivalent law. And he thinks that it's a discovery, ultimately, of science that we have these kinds of laws applying towards what we call the future and not towards what we call the past. And Craig Callender, in a paper reflecting on both Watanabe and Sober, says that ultimately what they show is that one, in general, cannot add non-trivial backward transition probabilities to a theory that already has non-trivial future transition probabilities. Now, a classic example of these would be, of course, quantum mechanics, but also we can think that the same general idea applies in statistical mechanics as well. So in the context of quantum mechanics, we see a quite analogous argument to that of Sober and Watanabe in Roger Penrose's book, The Emperor's New Mind. He uses this general line of reasoning to argue that quantum mechanics is a time asymmetric theory and ultimately a time-directed theory. So Penrose's setup is very simplistic. It's as follows. So we have at A, we have a light source emitting photons, and then we have a half-silvered mirror at 45 degrees to the beam of light, and then we have two detectors at 90 degrees of each other, C and D, and if the system is tuned just right, we will get the following statistics for a particular photon emitted from A, namely that it has 0.5 chance of being detected at C and 0.5 chance of being detected at D. So Penrose says that what we get here is two sets of conditional probabilities. So the probability of detection at C given emission at A is 0.5, and the probability of emission at A given detection at C is going to be 1. And similarly, the probability of emission at A given detection at D is also going to be 1. And he concludes from this kind of asymmetry that it's only for calculating the probabilities of future states on the basis of past states that quantum mechanics works. On this basis, quantum mechanics cannot be a time-symmetric theory. And using this general setup, Frank Arntzenius, in a series of papers, argues that forwards transitional probabilities are invariant under a change of initial conditions, but backwards transitional probabilities are not invariant under a change of initial conditions. So if we introduce a fourth box here, call it B, and we imagine that this is an alternative light source to A, then we can see that switching the light source from A to B does not change the probability of the detection at D and C, again given that the system is tuned in the right way. And Arntzenius uses this fact to support the claim that quantum mechanics is what he calls proto-causal but not retrocausal. And he says that our most plausible theories of such transitional frequencies, including quantum mechanics, entails that time has an objective direction. Now, in later papers, Arntzenius slightly weakens this claim by thinking about situations where such an asymmetry can indeed be due to background boundary conditions, in which case he says that an existence of an asymmetry in boundary conditions does not necessarily amount to the existence of an objective direction of time. But that particular issue is not going to affect the discussion in this paper. So to summarise the various versions of this argument, I'm going to put together a kind of master version of this argument. So premise 1 holds that probabilistic time translation invariant laws can only hold in one temporal direction. In effect, they are time-directed. Premise 2, our best physical theories, for example quantum mechanics, holds that the world possesses probabilistic time translation invariant laws. And our first conclusion from these two premises by inference to the best explanation is that our world possesses time-directed laws. Now premise 4, if our world possesses time-directed laws, then time has a privileged direction, namely from past to future. And so our final conclusion is that from premise 3 and 4, time has a privileged direction. So I'm going to question this argument based on premises 1 and 4. And though I go through both premises in the paper, in this talk I'm going to focus on my objections to premise 4, because that's where our reflection on the C theory, on a temporally adirectional metaphysics, gives us our main line of response to this argument by denying premise 4. So I'm going to argue that the C theory holds that we can perfectly well understand time as adirectional, as undirected, whilst holding that the world has a preferred time-directed description. So you might recognise this guy. This is John McTaggart, Ellis McTaggart. And McTaggart very famously introduced the A series and the B series. And the A series, as anyone that's done Introduction to Philosophy of Time will know, is the series of positions in time running from the past through the present and then to the future. Whereas the B series is an ordering of things in time in terms of earlier and later. Now, these might just sound like two different ways of saying the same thing, but there's very different metaphysical entailments of the A series and the B series here. And that's because the A series of the events in the world changes over time, whereas the B series does not. So if we imagine an ordering of World War I and World War II here, we can see there was first a time when World War I was present, and then there was the time when World War II was present and World War I was past, and now of course we take them to both be in the past. But we can see this change in the A series all the while. It's always the case that World War I is earlier than World War II, and there's no sense in which that changes. So crucially, there's a change in the A series but no change in the B series. Now, McTaggart also introduced a third series called the C series, and he's talked about this quite briefly in his original paper on the unreality of time, but he talks a lot more about it in his book The Nature of Existence. But in his paper, he says that the C series, while it determines the order of some set of events, it does not determine their direction. So we can think of the ordering relation of the C series as being something like temporal betweenness, something that gives a undirected ordering of some set of events, whereas the ordering relation of the B series is of course the earlier than relation. So here's another quote from McTaggart to give the idea of what's going on here. We have these four events, M, N, O, P, located at different times, and they're ordered in the C series such that N is between M and O is between N and P. So this gives us a C series, as he says, which runs M, N, O, P. Now, if this is the case, he says, then the B series from earlier to later can run either M, N, O, P, like this, so that M is earliest and P latest, or else P, O, N, M, so that P is the earliest and M is the latest. So we have this idea here that for every C series, there's two possible directed B series. The C series, in effect, underdetermines the B series of some set of events. So whereas traditionally the philosophy of time distinguishes between these two pictures, the dynamic picture of time and the static picture of time, where the dynamic picture of time has a privileged present moment that moves towards the future, and there's no such thing on a static image of time, what we're considering here is the difference between a directed and an adirectional universe. A directed universe which goes from some state to another, and an adirectional universe which doesn't really have any basic sense in which some events are really earlier than others. Rather, they're just given this adirectional betweenness ordering in time. Now, various people have defended something like the C theory of time. I discuss these in my Philosophy Compass paper, C Theories of Time, which is referenced at the top of this page here. A couple of prominent ones are Hans Reichenbach and Thomas Gold. So Reichenbach says that in the case of time reversal invariant theories like classical mechanics, since it's always possible to construct a converse description, that is, a description of a process relative to negative time, such as from future to past, then he says that positive and negative time supply equivalent descriptions, and it would be meaningless to ask which of the two descriptions is true. So he says that there's no real difference between describing things from earlier to later or from later to earlier. What we're ultimately doing when we're giving such time-directed descriptions is giving two different equivalent descriptions of the same underlying undirected reality. And Thomas Gold says that the description of our universe in the opposite sense of time, from future to past, though it sounds very strange, it has no conflict with any laws of physics. Our strange description, the future to past one, is not describing another universe, or how this universe might have been but isn't, but it is describing the very same thing. So the idea that both Gold and Reichenbach are putting forward here is that positive and negative time So describing things from past to future or from future to past merely give two different equivalent descriptions of the same world. Right? They're not describing different ways the world could actually be. They're just two different modes of description of a single possible world. So this is the basic idea behind the C theory, behind the idea of adirectional time that I want to put forward here. The idea that when we describe things in time-directed ways, that's not ascribing a preferred time direction onto time. When we give a time-directed description of the world, it is simply that. It is simply a description. There may be some particular reason for which we might prefer to describe the world from past to future rather than from future to past, but these two different sets of descriptions are not ultimately disagreeing with any basic temporal facts about the world. So Reichenbach elaborates on this at a few points in his book. He says that ultimately it has no meaning to say that, for example, entropy really goes up or that its time direction is really positive, because relative to backwards time, entropy goes down over time, and there's no further fact as to whether time is really going forwards or backwards. So we could, in principle, choose to describe everything from future to past. We would not be saying anything different about the way the world works. And as I say, this does not preclude us from just preferring to adopt the conventional description, that is, describing things from past to future. Okay, so now we can go back to apply some thoughts about adirectional time, about the C theory, to this one-way applicability argument. So here, premise 4, if our world possesses time-directed laws, then time has a privileged direction. But we've seen that the C theory holds that in principle we can perfectly well understand time as adirectional, whilst holding that the world might have a preferred time-directed description. So here's a case in point. Whenever we think of some paradigmatically causal process, such as the shattering of a wine glass, there's always going to be a preferred time-directed description, namely the one in which the cause precedes the effect. So this is something I've argued in some detail in my paper Causation and Time Reversal. There I argue that C theorists should hold that ultimately there is just a preferred time-directed description for macroscopic systems. So forwards and backwards descriptions of the world equivalently represent a single world, with some underlying temporal betweenness facts which give the basic time order of things. But it does not follow that the C theorist has to say that there's no objective direction of causation. When we look to the images on the left here, there's something very different about the familiar description of the process on the top here and the unfamiliar description of the process at the bottom. If we describe things from cause to effect, what we see is a shattering wine glass over time. Whereas if we describe from effect to cause, what we see here is random pieces of shattered glass kind of spontaneously jumping together to form a smooth wine glass. Now, a key thing, and maybe quite contentious thing that I argue in this paper, Causation and Time Reversal, is that when we do describe things backwards in time, when we describe the world from future to past, we are nonetheless describing the same ordinary causal processes. And really the key thing here is that this top description of the process here seems to accord to a simple causal explanation, namely the shattering of a wine glass. Whereas the bottom description does not. At least at face value, it seems to describe a series of coincidences, right, of these independent shards of glass all just happening to spontaneously jump together at the same time so as to form a smooth wine glass when evolved forwards over time. This clashes with intuitions about probability that we have. Secondly, it isn't the kind of thing that we humans can do. That is to say that we can very simply smash a wine glass by dropping it or throwing it at a wall or something like that, but there's no similar thing that we can do to unsmash a smashed wine glass. Which ultimately entails that regardless of which time direction we use to describe this process, we ultimately get back the same natural or empirical causal direction. Discussing this kind of case in his book The Direction of Time, Hans Reichenbach says that if someone argues that it's a matter of convention to select the direction of growing entropy as the direction of time, their conception cannot be called false, but they must not commit the error often connected with other forms of conventionalism, namely the error of overlooking the empirical content associated with the use of this convention. So the idea here is that the forwards in time descriptions here may be simpler or more natural than the backwards in time descriptions, but it doesn't follow that they are any more true. Recall that the C theorist holds that forwards and backwards time describe the same world. They don't describe different worlds. So if there is some preferred set of causal direction facts here, which we think that there clearly are, given that the top picture seems to describe natural causal processes, whereas the bottom one seems to describe this really problematic, improbable, coincidental, conspiratorial of recombining of fragments of wine glass. Ultimately, regardless of whether time is really going forwards or backwards, there's a reason to prefer the top description. So such processes and the laws that govern them are ultimately reasons to prefer one set of time-directed descriptions over their converse. So on the C theory, we can understand this as empirical grounds for picking the past to future direction as the natural means of describing processes. This does not require past to future and future to past descriptions to refer to or represent different possible worlds, and therefore this particular fact does not require us to commit to the extra structure of a direction of time. And just to finish off here, we can have a quick look at the other possible way of responding to this argument, which is to consider whether the relevant asymmetry here comes from an asymmetry of pre-selecting and not post-selecting data. So behind Penrose's contention that quantum mechanics is time asymmetric, or indeed time directed, he has this assumption here, this background intuition. So he says that if the photocell indeed registers, so that is to say if one of C or D registers a photon, then it's virtually certain that the photon came from the lamp and not from the lab wall. But why is this? Well, this is only because we've set up the system in such a way that we have one possible source of a photon. But of course, if we had a second possible emitter here, and we had A and B set up so they were kind of randomly emitting photons, and all we had was information as to whether a photon was detected at D or C, then we would no longer have it the case being virtually certain that the photon came from the lamp. Indeed, Craig Callender says that if Penrose is genuinely concerned with the issue of time reversal invariance, with the issue of whether quantum mechanics is time symmetric, then he should really treat the emitter as a receiver and vice versa. That is to say, if what we have is the fact that there is a photon registering at C, then to think of the time reversed equivalent of this, we should treat C now as a emitter of a photon, and then treat A and B as possible receivers of that photon. And if we run the probabilities based on this, then what we get is 0.5 detection at A and 0.5 detection at B. So ultimately, if we're conditionalizing our statistics purely on the time reversed equivalent of an emission at C, then we should get a 50-50 distribution over detection at A and B. And this ultimately matches with the statistics of a post-selected only ensemble. That's a statistical ensemble where in every case what you have is a photon detected at C. And this idea of using post-selected ensembles and indeed pre-selected and post-selected ensembles is a key idea behind time-symmetric accounts of quantum measurement, such as in the famous paper by Aronov, Bergman and Lebovitz. And indeed the idea of post-selected ensembles is a key aspect of quantum retrodiction, such as in this paper here by Pegg and Barnett. So there's various work on time-symmetric quantum mechanics and quantum retrodiction, and one feature of this is if you only concern yourself with post-selected ensembles, then you have the Born rule applying perfectly consistently towards the past as opposed to towards the future. So if you do select your data in the right way, you can ultimately have your backwards directed time translation invariant statistical laws towards the past. But none of that is to say that there isn't some basic asymmetry in our world. And that is to say that we can prepare systems, not just pre-select, but actually physically prepare systems so that we do have forwards in time directed time translation invariant probabilistic laws, but there doesn't seem to be any clear way in which we can post-pair a system, that is, set up an experiment so that we can have some particular fixed final condition or outcome or result, whilst also having a genuine openness as to the initial state. But this is something which I'm not going to get into in this talk, but if you are interested, you should soon be able to read a long-form draft of this paper, so do get in touch. But to summarise what I presented, I've argued that at best the one-way applicability argument shows that it's preferable to hold that the world is better described by future-directed probabilistic laws than past-directed probabilistic laws. This is ultimately a consequence of the broader fact that the past better explains the future than vice versa, which perhaps we can put down to the thermodynamic asymmetry and maybe due to some asymmetry in the temporal boundary conditions of the world. But all of this is perfectly consistent with the C theory, the idea that the past to future and future to past descriptions pick out a single possible world rather than representing two different ways the world could actually be. And therefore we do not require the extra structure of a direction of time to make sense of the world's preference for forwards in time probabilistic laws.